Synthesis of selenium nanoparticles using sodium selenite Se, 4, as a precursor and titanium, 3, chloride as a reducing agent. Abstract, a novel, simple, rapid and inexpensive wet chemical method has been developed to synthesize selenium nanoparticles by reduction of selenium, 4, using titanium, 3, chloride as a reducing agent in acid medium at room temperature. The method is capable of producing selenium nanoparticles in a size ranging from 40 to 90 nanometers under ambient conditions. The synthesized nanoparticles have been characterized by UV-Visible Spectrophotometry, X-ray diffraction, XRD, energy dispersive X-ray, EDS, dynamic light scattering particle size analyzer, DLS, scanning electron microscope, SEM, and transmission electron microscope, TEM, techniques. Crystalline selenium nanoparticles were obtained without post-annealing treatment. Keywords: selenium nanoparticles, titanium, 3, as reductant, synthesis and characterization. Introduction. Selenium is well known for its photoelectrical and semiconductor 1 properties and high reactivity towards a wealth of chemicals 2. Therefore, it finds numerous applications in several photoelectrical devices, solar cells, xerography 3, and in the production of functional materials 2 such as Ag2Se, ZnSe, CdSe etc. However, the nanoselenium particles or fabricates are found to be associated with a large number of properties such as relatively low melting point, a high photoconductivity, high catalytic activity, towards hydration and oxidation reactions, high refraction coefficient in devices and relatively large piezoelectric, thermoelectronic and linear optical responses 4,5 compared to its bulk material. Hence, nanoselenium fabricates find broad applications in photoelectronic devices, photovoltaic cells, rectifiers, photographic exposure meters and xerography 4,5. Colloidal/nanoselenium has been employed in the preparation of nutritional supplements 6 and developed for applications in medical diagnostics 7, and in some biological activities 8. Thus, the synthesis and characterization of selenium nanoparticles have caused the greatest interest to researchers. A survey of literature reveals that the main nanofabrication methodologies adopted in preparing selenium nanoparticles are based on the chemical reduction of higher valent selenium to zero valent selenium using a suitable reductant based on bottom-up approach. In most of these methods selenium, 4, in the form of sodium selenite, selenous acid, or selenium dioxide, as a precursor, is reduced to elemental selenium in nanocrystalline form employing various reducing agents such as dextrose 9, sodium ascorbate 10, ascorbic acid 11,12, hydrazine 13,14, hydrazine hydrate, in the presence of polyvinyl pyrrolidine, 15, sodium metabisulfite, in presence of sodium dodecyl sulfate, 16, sodium thiosulfate, in presence of surfactant stabilizer, 16 glutathione 17. Polyvinyl alcohol 18 etc. Other methods of producing nanoselenium include irradiation technique 19, ultrasonic 20, and laser ablation approaches 21, micelle-mediated 22 and electrochemical synthesis techniques 23, a fermentation procedure, in which probiotic lactic acid bacteria is made use of, 24 etc. The nanoparticles prepared with these methods are mostly spherical or quadrate in nature. A careful delve into these methods reveals that most of them suffer from one disadvantage or the other. For example, the methods involving dextrose 9, hydrazine 13,14, glutathione 17 as reductants are tedious and time-consuming, while those with hydrazine hydrate 15, sodium metabisulfite 16, and sodium thiosulfate 16 need the presence of some reagents, mentioned above in parenthesis, to stabilize the nanoselenium particles obtained. The reduction of selenium, 4, by sodium ascorbate 10 or ascorbic acid 11,12 is extremely slow and requires about 5 HRS to realize the formation of nanoselenium. The reaction with polyvinyl alcohol 18 must be carried out at elevated temperatures, 1400 C for 48 HRS. The other types of methods cited above 19-23, besides being tedious, necessitate use of the expensive state-of-the-art technologies imperative, and to provide appropriate culture medium for the growth of bacteria is a difficult task in the fermentation procedure. 24. In the present paper, we demonstrated the use of titanium, chloride as a reducing agent to generate selenium nanoparticles, and the procedure is free from the drawbacks of the earlier ones mentioned above. The method consists in treating aqueous solution of sodium selenite selenium, taken as a precursor, and hydrochloric acid medium with titanium, chloride solution as a reductant at room temperature. The method is simple, inexpensive, the reduction reaction is rapid, and selenium nanoparticles of technologically useful range can be synthesized. Further, this method involves the use of all inorganic reagents, which are available in a high state of purity and hence can be easily and completely washed away from the selenium nanoparticle in the ambient aqueous medium by rising with distilled water. Moreover, the authors proposed the debut of titanium, chloride as a reducing agent for the synthesis of selenium nanoparticles. Results and discussion. The reduction of sodium selenite or selenium, to zero charged or elemental selenium with titanium, chloride in hydrochloric acid medium takes place according to the following chemical reactions. Titanium, chloride is only a mild reducing agent under normal experimental conditions. A survey of literature reveals that the reduction of selenium, by various reductants were found feasible in hydrochloric acid medium or in presence of chloride ion 3032. Therefore, in the present investigation, selenium nanoparticles have been synthesized in the above acid medium containing chloride ion and in presence of a slight excess of titanium, chloride to ensure complete reduction of selenium, by titanium, chloride. Characterizations of selenium nanoparticles. The formation of selenium nanoparticles in presence of hydrochloric acid medium is primarily authenticated X-ray diffraction spectrum. The XRD pattern obtained from the S-prepared nanoparticles is shown in Figure 1. All the diffraction peaks in the XRD pattern could be indexed as the trigonal phase of selenium nanoparticles. All the peaks can be readily indexed to crystalline trigonal selenium, TSE, JCPDS 6-362, as a comparison. Although the diffraction peaks from XRD patterns of the raw selenium powders can be well indexed to trigonal selenium with the P3121 space group, the strong diffraction intensity of the 101 peak is indicating the trigonal selenium, TSE. Further, there is no clear change in peak positions, as well as the absence of additional peaks indicate that the sample crystallizes in single-phase trigonal structure. The average crystal light size of pure selenium nanoparticles was calculated using Debye-Scherrer formula 3335 L equals 0.92/b cos, where L is the crystal light size. The X-ray wavelength, the Bragg diffraction angle, and SS, the full width at half maximum, FWHM, and found to be about 65 nanometers. Figure 1. XRD pattern for selenium nanoparticle. From UV-Vis spectra shown in Figure 2, it is observed that the dot max of the selenium nanoparticles was observed at 311 nanometers at lower concentrations, whereas in higher concentrations no specific dot max could be identified, rather a steady increase in absorbance from 800-300 nm had been observed. The UV-visible spectra are in comparison to that of the selenium nanoparticles prepared by reducing with hydrazine hydrate 36. Form of the produced nanoparticles, SEM, TEM, and EDX studies. The formation of selenium nanoparticles was verified by the corresponding SEM images presented in Figure 3. The selenium particles were found to coarse and irregular but well separated. It is well accepted that the formation of crystals is mainly achieved through two stages, nucleation and growth. As soon as the reaction starts, a certain amount of TSE seeds immediately precipitated out, i.e., nucleation, due to the reduced solubility of Se in the solution. The formation of these TSE seeds relieved the level of supersaturation, and the following growth of residual ASE colloidal particles present in the solution would occur on these TSE seeds. Therefore, we reason that the strong dependence of the morphology of TSE on the amount of SE in DEG solution should be ascribed to the variation in the amounts of both ASE colloids and TSE seeds. The TEM images shown in Figure 4 reveal the agglomeration of the particles in solid phase, whereas in liquid phase there is a well separation of selenium nanoparticles. SAED pattern of TEM images. The SAED images obtained from TEM studies clearly indicate that selenium nanoparticles are crystalline in nature. This is because the decrease in the viscosity of the medium, 2mHCl, allows the dissolution of amorphous selenium particles in the solution to be deposited on the few trigonal selenium seeds which are expected to be formed in the reaction medium. The EDX spectra of the pure selenium nanoparticles is shown in Figure 5 and shows the peaks of pure selenium. Particle size distribution. From Table 1 and Figure 6, the diameter histogram of the particle obtained from light scattering particle size analysis in the solution form. Nearly 94% of the selenium particles were found to be below 100 nanometers in size, and the average size of the particles was found to be around 60 nanometers. 3. Experimental section. All the reagents used of A are grade unless and otherwise stated, and the solutions were prepared in double distilled water. A 0.25 m solution of sodium selenite Na2CO3 was prepared by dissolving the required quantity of the salt in distilled water in a 100 ml standard flask. Similarly, a 0.75 m solution of titanium, 3, chloride was prepared from 30% titanium, 3, chloride solution in presence of hydrochloric acid medium in a 100 ml standard flask. A 10 ml of 0.25 m solution of sodium selenite was taken into a 250 ml beaker. To this solution enough titanium, 3, chloride and hydrochloric acids were added such that their overall concentrations are about 9 m and 1 m respectively when the solution is diluted to 100 ml. To this reaction mixture about 25 ml of titanium, 3, chloride solution of 0.75 m was slowly added while it is being stirred mechanically on a magnetic stirrer. The stirring of the solution was continued for about 10 minutes to ensure the complete reduction of selenium, 4, by titanium, 3, chloride. The red viscous solution was then centrifuged, the precipitated selenium was collected, rinsed about 5 times with distilled water, followed by absolute ethanol, acetone, and diethyl ether. The substance was then dried at about 400 C for 2 hours and taken for analysis. Spectral studies were made using a thermoscientific evolution 201 model UV-Visible Spectrophotometer. XRD patterns were obtained on a Philips Expert MPD X-ray diffractomer using CU-Ca 1.054059A, radiation with the X-ray generator operating at 45 kV and 40 mA. SEM images were obtained on JEOL 2010 microscopes. The particle image measurements were conducted on a Hitachi H700H Transmission Electron Microscope, TEM, operated at 150 kV accelerating voltage. TEM samples containing nano-selenium particles were prepared by dip coating of the dispersed colloidal solutions on formbar/carbon film CU grids, 200 mesh, 3 mm, Agar Scientific Limited. Energy Dispersive X-Ray, EDS, analyses have also been conducted on the sample particles to verify their composition and purity. The resulting dispersions of selenium nanoparticles at various growth stages were subjected to the measurements for their structural images. It reflects the variation of particle mean diameters over a period of time due to agglomeration. Conclusions. In summary, we have provided a convenient and fast approach for the preparation of selenium nanoparticles by reducing sodium selenite, Se4, using titanium, 3, chloride as a reductant in 2M hydrochloric acid medium. This method is simple and inexpensive for producing selenium nanoparticles for various applications. Acknowledgements. The authors are grateful to the authorities of Andhra University for the research facilities provided for undertaking the work and Dr. B. Kishore Babu for the work done on SEM and TEM images of selenium nanoparticles. Further, the authors wish to thank the authorities of Department of Engineering Chemistry AU College of Engineering, A, Andhra University for carry out this research.